Dear customers, dear viewers and guests, dear friends of course, I would like to welcome you to our webinar, Optimizing PVC Formulations and Management of Critical Variables During the Process. My name is Giorgio Critelli and my role is Bausano US General Manager. As Bausano, we have a branch in United States in the Chicago area, and I personally manage this branch. As I mentioned before, in the Chicago area. Over there we have the service and the spare parts available. And we also have the commercial and after-sales department. As Bausano, our headquarters is in Ruotolo Canavese in the Turin area. And we also have facilities in India and in Brazil. Today we are here in the Bausano laboratory where all formulation are, where we test all formulation. And we are here with Alessandro Ruotolo, our plastic expert and the process engineer.
Good morning, everyone.
And after that, we are going to meet also Andrea Basolo, materials engineer and also plastic expert. Alessandro is also our screw designer. And they will be our speakers for today. I would like to start by thanking you for attending today's live event, which will be divided in three parts. The first part will be a theoretical section where we analyze the PVC formulations. And after that, we are going to analyze 4 different formulations, focusing on how stabilizer and the additives we can add in this formulation and the impact in the final product. After that, we are going to have a practical demonstration with the Bausano laboratory, focusing on the rheological characterization using the rheometer and the plastograph. And we are going to focus also on the screw design and how the screw design can change the quality and the production rate. And the final part will be the question and answer session. I need to inform you that we organize this webinar with the collaboration of Reagents SPA, a global scale manufacturer of specialty chemicals for PVC and thermoplastic. Together with Reagents, we collect this information and why Reagents is the perfect partner for us. Because thanks to the global scales presence of reagents worldwide, and thanks to the using of reagents of the Bausano laboratory worldwide, for example in their facility in Italy, in India, and United States, make them the perfect partner for analyzing and optimizing PVC formulation. Now, before we switch to our expert, and before we dive into the discussion, ladies and gentlemen, as always, I would like to give you some information about your question. In order to answer to your question, please punch the button located on the bottom of your screen. Punch in that button and you are all set. We will answer to all your questions and that's sent by chat or by email during this webinar, and we will answer to all your questions. Now I'll give the floor to Alessandro.
Thank you, Giorgio. Yes, as Giorgio mentioned before, I'm Alessandro Ruotolo and I'm the lab manager here in Bausano. And today, together with my colleague Andrea Basolo, we'll show you what we prepared for this webinar. The main topic is the PVC, of course. We analyzed 4 different families of recipes of PVC. We have the rigid PVC pipes recipes, rigid PVC for fitting recipes, rigid PVC for window profile recipes, and the plasticized PVC for medical application. Together with all our colleagues from the technical part, we decided to focus on what we call critical variables. There are basically additives present inside each formulation that, according to our experience, better represent each recipe families. Then, after this analysis, we will see how Bausano, through what we call the Bausano method, manage these recipes, and according to each specific material, optimize the screw design dedicated to the process of those materials, both on lab and industrial scale. Let's start with the first recipe. The first recipe is UPVC pipes. Here we show two standard recipes. The first one is for a pressure pipe, and the second one is for sewer pipe. Here in red, we highlight the critical variable that we choose. There is, in this case, the calcium carbonate amount. As we can see from the slide, we have a lower amount for pressure pipe. Why? Because in case of pressure pipe, of course, we need to increase the mechanical properties of the material in order to pass the Barnes test. Yeah. And then we have a higher percent of calcium carbonate in case of sewer pipe. And as we can see from the following slide, this difference will affect the rheological materials, and then also the melting time or melting energy required to get the whole melting or gelation of those two different materials. Then, together with all the other additives, here we highlight in blue as well other two variables that for us are very important. That is the percent of calcium stearate and the percent of paraffin wax. Why? Because we know that calcium stearate has the aim, the target to anticipate the gelation inside the formulation, and together with the paraffin wax can avoid the stickiness of the material on the screws and on the barrel wall. And this is very important, especially for tin-based stabilizer recipe like the ones that we are showing in this moment. We know that tin-based stabilizer increase the stickiness of material on the screws, and then we need a higher amount of calcium stearate and paraffin wax in order to get the better flowability of material on the screw and inside the extrusion die. Now we show you the results of the rheological characterization through the Brabender plastograph. Here we have in red the graph related to the sewer formulation, and in blue the graph related to the pressure formulation. As we can see, usually conventionally we have that the melting time that is proportional to the melting energy required to get the whole gelation or melting of the material inside the measuring chamber of the plastograph is the point in which the graph changes the slope, and the value, the torque value on the Brabender rotor start decreasing up to constancy. And then here on the vertical line, here we have highlighted the two melting time in two different cases. As we can see, we have an important gap between the melting time of pressure and sugar. And this difference is due especially to the higher amount of calcium carbonate in case of the sewer pipe.
Okay, Alessandro, actually, I have a question for you. I'm just wondering, what is the implication if we have an early gelation or a delayed gelation? I mean, we have some better quality if we get an early gelation or a delayed gelation?
This is a good question. Thank you, thank you, Giorgio, for this question. Yeah, I wouldn't like to talk about better or worse quality. I mean, in this case, we know that according to the gelation time or gelation energy required from every single specific material, we have to configure a different extruder in terms of barrel length,
okay,
or in terms of screw design. Usually for higher melting time or energy, we need a longer barrel, and we need high compression and shear screws. For anticipate, so for short melting time, usually we use short LD ratio and low compression screw. Of course, it can affect the quality when we process the material on the worst extruder.
Yeah.
For example, if a material that is characterized by lower melting time, process on an extruder with a high shear and high compression ratio with a long barrel, can lead to degradation due to mechanical and thermal reason.
Okay, Alessandro, just another one about this topic. If I'm correct, you mean a different LD ratio between, for example, one gelation and another gelation. And in accordance with the adding of stearite, calcium stearite, one of the purpose of the calcium stearite could be to use the same pair of screw for example, two different gelation. For example, I mean, we have two different gelling material with two different, for example, one material reach one kind of gelation, another material reach another kind of gelation. Adding the calcium stearite can help us in order to use the same pair of screw.
Yeah, thank you. This is as well a good question. Yeah, Giorgio. Yeah, this is not the main purpose because, as I mentioned before, the main purpose is anticipate gelation and avoid stickiness for team-based recipes in this case. But then, as a, let's say, secondary consequence, yeah, of course, the use of a certain amount of calcium stearate can anticipate the gelation point of the, for example, in this case, of the sewer formulation, making it closer to the point that characterizes the pressure pipe. Yeah. And in this case, of course, it's easier to process both the material with the same screw configuration. Okay. Maybe changing a little bit the temperatures or the extrusion speed. Yeah.
Okay.
In order to avoid to get the worst quality of the material.
Okay.
Thank you. Let's go on. Now we show the second recipe family that we choose is the fitting unplasticized, so rigid PVC. And also in this case we have two families. The first one is the pressure fitting, and the second one is the sewer fitting. We have let's say a parallel situation if compared with the pipe. Even if some of the additives are a little bit different. Also in this case, we decide to focus on the critical variable, that is the calcium carbon amount. In this case, as well as for the pipe, we have a lower amount of calcium carbon in case of pressure fitting, always to increase the mechanical properties and reduce the risk of not to pass the bars test, and a higher calcium carbon amount in case of sewer. Also in this case, this difference makes a slight difference also in the rheology and then in the melting time or energy required to get the proper gelation of the two recipes. Here highlighted in blue are always calcium stearate and paraffin wax. Why? For the same reason of the formulation of pipe. Why? Because also in this case, calcium stearate anticipates gelation, and together with paraffin wax allows a better flowability of material in case of tin-based stabilized recipes. Then from the table we see that together with the usual additive that we have also for pipe, here in this case for fitting we have added impact modifier, processing aid, internal lubricant, and especially this last one is needed in order to increase the flowability of material inside the mold.
Actually, Alessandro, I have another question for you. Sorry about that. I'm just thinking, if I'm correct, adding paraffin wax and calcium stearate is going to improve the quality in the gelation. But I'm thinking, cost-wise, could have a too high impact using this kind of additives?
This is another good question. Of course, this could be very interesting for the viewers and our customers.
Thank you.
They are very interested on the cost, of course, of formulation. Yeah, of course, adding those additives in a certain amount, of course, represent a cost for our customer. But at the same time, those additives allow customers to go on working with the same recipes. Okay. For example, in this case, tin-based stabilized recipes, without any problem of stickiness or reduction of quality of material. Okay. And it could be important also in terms of costs, because, for example, they are not forced to switch from tin-based stabilizer to calcium zinc stabilizer that in certain cases or for certain market can represent a higher cost for the plant.
Okay, if I understood, it has a cost, but comparing with the other cost of changing stabilizer is much better.
Yeah, okay. Exactly.
Thank you.
You're welcome. Now, we show also in this case what we have in terms of plastograph result for the fitting, both pressure here, the graph in blue, and sewer, the graph in red. In this case, we see that we have a gap between the melting time, as well as we had, as we mentioned before, for the pipe. In this case, if you remember the previous slides, the difference is not exactly the same. The gap is reduced. Why? Because of the effect of different additivation in different amount if compared with the previous pipe recipe. Here we have the effect added of internal lubricant, of processing aid, of impact modifier, that makes the gap to be a little bit lower. Now, I give the floor to my colleague here, Andrea Basolo.
Thank you, Alessandro. Okay, so the next topic of this webinar is another family of PVC compounds, that is the PVC compound for unplasticized PVC profile for, the unplasticized PVC compound for window profiles. So in this case we have a PVC resin K666. It means that we need to have, let's say, long molecular chains because we need good mechanical properties. We have for that a small addition of calcium carbonate, just 10 parts. It means that we need some more stiffness, but we don't want to compromise the mechanical properties of the profile. We have some titanium dioxide to give the white color. Impact modifier, obviously, again, to have good mechanical properties. But what we found as, let's say, critical variable is, in this case, the heat stabilizer. So we have the first column, you see, the formulation is stabilized with a tin-based heat stabilizer. In the other column, you see a calcium zinc heat stabilizer. What is different is what you see underlined in blue. And so the compounds, the components used for lubrication, because as Alessandro said before, tin-based heat stabilizer make the melt more sticky, and so you can undergo the problem of, let's say, the material tends to stick on the screws. It passes inside the calendar gaps between the two screws in a counter-rotating twin-screw extruder, and so the mechanical work is higher. So we need to increase let's say, the lubricants, and in this case, for example, we add the calcium stearate, paraffin wax, and some oxidized polyethylene wax. In the other case, with the calcium zinc heat stabilizer, we work on a one pack. So it means that is a, as the name say, one pack in which you have the calcium zinc stabilizer and all the lubricants. In this case, we have a small addition of paraffin wax, but let's say with just one component, you can replace 4 components. It's also easier while mixing all the powders. And if we switch to the other slide, in which we see the Brabender results, actually, okay, we have a gap between the two vertical lines. So it means that with calcium zinc, you have a slightly longer time needed to completely plastify the material. But actually, if you look at the shape of the curves, it's similar, and that's quite obvious because the formulation is made for customers who want to switch from one compound to the other one without changing the screws. Obviously, if I am a producer of profiles, I would like to work all the formulation on the same machine. So that's why the formulation are pretty similar. Now we switch to another field, that is the medical field. In this case, we have a PVC, plasticized PVC formulation, in which we have a resin that is a K70. The use of resin with high K numbers is important because high K numbers allow the material to absorb correctly the plasticizer while mixing. We have a compound that is called Rheological. It's a heat stabilizer. Has really a very small amount of polyethylene wax, and in both cases 60 pHr of plasticizer. What is interesting is that in this case, if you compare with the previous formulation, we have a very lower amount of lubricants because the plasticizer acts itself as a lubricant. And the aim of this comparison is to compare two kinds of plasticizer. One, the DOP or DEHP that is, let's say, in some fields it can be still used, but there are many and many restrictions every year because it has been found to be harmful for the human health. And another plasticizer that is called bioplasticizer. It's an alternative to other plasticizers, like for example DIDP, DINP, that have a slightly higher molecular weight, and so they tend not to migrate as DOP does. BOP plasticizer is let's say a derivative of epoxidized soybean oil, but with some modification to the chemical structure in order to avoid one of the main troubles that we have with soybean oil, that is the exudation when high concentrations are reached. And so that's why we have this comparison. Also in this case, if we see the comparison between the Brabender graphs, we see that the melting time is slightly higher with the bioplasticizer, but again, the difference is not so high because this plasticizer has been thought as a replacement, also as a green replacement, so as a replacement that which production does not rely on oil and so on. And so the aim is to make a product that can replace easily synthetic plasticizers without significant problems for the producer. So again, I leave the floor to Alessandro, and we go on with some conclusions. It's up to you.
Thank you, Andrea. Yeah, now briefly some conclusion. Yeah, let's say a summary of what we have just seen about the analyzed recipes, and what we have seen as variation of the critical variables that we individuate, and related to the melting energy. So for PVC pipes, here we have that the critical variable, the percent of filler, increase leads to increase of the melting energy required to get the whole melting of the volume of the analyzed material. For UPVC fitting, basically we have the same trend. So higher is the percent of filler, higher is the melting energy required to get the proper gelation or melting of material. In case of plasticized PVC medical, yeah, we have a direct correlation between the kind of plasticizer used and the melting energy, because the plasticizer is the only one variable that affects, basically, if you remember the formulations, the melting energy. So with the bioplasticizer, we have a higher melting energy required to reach the whole gelation of the analyzed samples. In case of DOP standard plasticizer, the melting energy decrease. Now let's talk a little bit about the Bausano method. I mean, when we have to configure a brand new screw design for a certain analyzed material, we start from the Brabender graph related to the analyzed material. Then we check all the screw designs that are already existing in our huge database, because you know, Andrea,
it's really huge.
It's very huge, and we are talking about more than 75 years of experience of Bausano, maybe even more. Then we have our database full of different screw design. Then we cross-check this database, of course, with the feedback that our customer gave us relating to the material that they usually process on our screws. Then, from this cross-analysis, we obtained the new screw design. We give you an example. For example, we have to configure a new screw design for a new material that is, let's say, a pressure pipe drive. What we do, we compare the rheology obtained through the plastograph of this material with the results obtained on similar materials of the same family. Then we check what are the best already used screws with the comparing material, and according to our analysis we configure the new screw design. For example, we can decide to use exactly the same screw design as the reference material, or maybe the reference material is characterized by a lower melting energy, and in this case as a screw design I can decide to increase the shearing of the screw or increasing the compression of the screw, changing the screw geometry. Now we show you what we obtained for the 4 recipes during the trials on the lab scale extruder MD30 in our Bausano lab. We detected the first screw model A13 as the best screw on the lab scale extruder configured for a rigid pipe recipe. This screw is characterized by 2.2 as maximum compression ratio before degassing and 1.4 as compression ratio after degassing in the final metering part. For rigid fitting and rigid window profile recipes, we found the screw model 802 characterized by 2, so a little bit lower compression ratio before degassing and 1.2 in the metering as the best screw design that we have in our lab for those 2 recipes. In case of flexible medical recipes, we know that this material has lower melting energy required to get the proper gelation if compared to all the others, and this result is in line with what we have checked on our lab.
Yeah.
Because the screw required for this purpose has the lowest compression ratio, that is 1.7 in before the gassing, and lowest as well in the metering part. In conclusion, what can we say, Andrea? We can say that, as we mentioned before, the rheological analysis of material play an important, fundamental role in the definition of the optimized screw design. We are talking about 2 main lab equipment for the rheological analysis. The first one is the rheometer.
Yeah.
Why do you smile? And the second
Nobody
one,
told me.
and the second one is the Brabender plastograph. The output data from those tools are used not only for the direct screw design definition, but also as input data for the software simulation that we are able to make on the material according to the geometry of single screw and die that are simulated on our simulation software. So through this analysis on the material, through the rheology of material, we can predict through the software simulation how will be the behavior of the analyzed material on a certain screw and die geometry,
Yes.
in terms of temperature, overheating, shears, and so on. Then, through this method, we will be able to minimize, of course, the errors, to face with all the customer or user issues and needs. And even more, we are able to anticipate the customers and user needs in terms of extrusion process on their main materials. Yes. Now, I give again
it's
the floor to you, Andrea. It's
Okay.
your turn.
Thank you.
You're
So,
welcome.
We talked about Barbender plastograph. We talked about capillary rheometer, and so now it's time to speak about it. So Barbender is known by, I think, everybody who works with PVC. The plastograph is a machine with a mixing chamber in which two screws are rotating in opposite directions, and obviously the mixing chamber is heated at a certain temperature that is decided by the operator, and the machine has a sensor on the shaft and collects the data of torque as a function of time, and gives the curves we saw before during this webinar. The other machine we have here in the lab is the capillary rheometer. Capillary rheometer, that is a machine able to give the viscosity of the material as a function of the shear rate. It's a characteristic of the material that depends on the shear rate. So for higher shear rate, viscosity is lower, and also on temperature. So for higher temperature, viscosity is lower. So what is done is to make three curves in general at different temperatures. So to see this dependency on time. And then these viscosity curves that appear as we see on a logarithmic graph scale, we can use this data for mainly two applications. One is to design the extrusion dies, and so we have software able to make if-IM simulation of computer fluid dynamics, and so we can see how the material pushed by the pressure built up by the screws moves inside the die, and so we can see, for example, if we have zones in which we have stagnation, that is, harmful for PVC. PVC must move forward always, otherwise it burns. So it's better to be sure that the die is designed correctly. The other application is to model single screw extruders. So we have software that are able to see a lot of parameters like shear rate, temperature, viscosity, and so on along the screw axis. And so again, it helps us in the design of the proper screw geometry. But now, I think we have talked a lot, so let's see something practical. I will show you how to work on the Barbender. So this one, as you see, is the Barbender. We will charge the material inside the hopper and see what happens during the test. So the material we will use, I will speak you later about the material we will use. We are working at 25 RPM of screw speed, and the mixer temperature is of 182 degrees. So we can start the measure. Okay. the temperature is good, so we can start. Okay. Then the machine takes some time to make the calibration to be sure that the measured torque is correct. Then we will pour the material here inside the hopper and then put this plung, and then the machine works automatically, and in 5 minutes, that is the time of this test, we will see the results. So okay, we pour the material, we put the plung and we push a little bit just to help it to enter completely inside the chamber, and most of all to have a cleaner peak, a cleaner first peak. Then later we will see what does it mean. Okay, here we are. That's good. So as you see, here we have a high peak. That means that when you put the material, obviously, a material which is solid, in a solid state, inside the mixing chamber, torque increases. But then the material, let's say, it organizes inside the mixing chamber, and it leads to a decrease of the torque that I think you are seeing now also live. After that, after a while, that depends on the characteristic of the compound, the torque starts to increase again, and then it stabilizes on a certain value. The distance in terms of time between the two peaks, it gives an indication on the behavior of the material, and so on how to process it when we will need it to extrude it. Some things about this material. This material is something we use to clean the extruders. So it's a PVC K67, and in the compound we have also calcium zinc stabilizer as one pack in very high concentration, that is something like 15 parts, that is really high. It means that we will have also, since we use a one pack, also a high quantity of low molecular weight lubricant that affects the gelation of the material, and so this gelation will be shifted to very long times. In addition, we have also 30 parts of calcium carbonate, and so we expect now to see a material that at this temperature does not gelify completely, because it's, as we saw before, very highly lubricated and very highly filled. And so, as we saw, these two parameters tend to shift the second peak to higher to longer times. And so now in 2 minutes and a half we will see what happens, but I know I made a spoiler. Meanwhile, let's see also something about the capillary rheometer. As I said, capillary rheometer is no, I didn't say nothing about that. We have two chambers here inside with two pistons. The pistons enters inside the chamber where the material is poured before the test and heated for a while. Then the pistons move at constant speed, and the speed varies during the test. Then when the steady state is reached, the data are collected. Data that are in terms of pressure. So here we have 1 and 2 pressure transducers that measure the pressure here inside the two chambers. We have also a temperature sensor that is, let's say, we needed to know the temperature of the capillary, which is this metal part, this one, that has a calibrated hole of, in this case, of 1 millimeter, and a certain length that in this case is of 10 millimeters. If we make a measure with this rheometer, the value we will get are of apparent viscosity. So it's not, let's say, the true viscosity of the material, but it's a value that depends on the geometry of the machine, of the testing machine, and of the capillar we are using. So for let's say, to avoid this problem, the test is done with the two chambers at the same time, using in one of the chamber one capillar with a certain length. In the other chamber, we use a capillar with the same diameter of the hole, but with a length that is more or less zero. It may be 0.1, 0.2 millimeters, but it is as much as possible close to zero. In this case, with the Bagley correction, we are able to remove the effects due to the geometry of the chamber, as I said, and have what we call the true viscosity, what is called the true viscosity of the material. That is the one we use for what I explained before, so for the designing of dies and screws. Here we have the test is finished, and so, as I said, we see the first peak after 10 seconds more or less, and the last peak, the X1, is got more or less at the end of the test. It means that the material hasn't plasticized completely, but that's something we knew because we have a high quantity of low molecular weight lubricant and filler that delay a lot the gelation of the material. So I think I have spoken a long time, and so I leave again the floor to Alessandro and Giorgio with some of your questions.
Thank you, Andrea.
Thank you, Andrea.
We can start finally the Q&A session. Time-wise, we got a lot of requests, and just for this reason, for timing reason, I just choose 4 or 5 of them, the easiest one. No, I'm just joking. Actually, I choose this one because when I meet you, gentlemen, many times I got this kind of question, and we have a chance today to get directly the answer from Alessandro and Andrea. The first one is, which is the best extruder for processing PVC, single or twin screw? And actually in Bausano we have both.
This is a very good question because, as well as for you, also for us, is one of the most frequent questions from our customers. It depends, of course. Why? Because, for example, if we talk about powder, so PVC, both rigid or plasticized dry blend,
yeah,
we are forced to use a twin screw. We strongly recommend to use a twin screw in order to avoid any possible lack of quality of the material, of the final product. So in this case, we will always use the twin screw. Also in case of additivation of additives directly inside the extruder.
Yeah.
For example, master batch or stabilizers, yeah, or lubricant. Okay. Because of the higher melting capacity of twin screw due to the intermeshing of the two screws. In case we start, for example, from PVC granules, yeah, we can process them as well on single screws with very, very good results, especially for a small technical profile, yeah, for example.
Because for bigger one, probably is better.
Yeah, for bigger one, we know that the pressure inside the die is a very important factor that can affect the final quality. In order to better uniform the pressure inside the die, sometimes it's strongly recommended the use of twin screw instead of single screw.
Thank you, Alessandro. The other one is what is the best feeding system for the extruder?
Also, this one is it's also a good question, of course, Giorgio. What we consider the best feeding system, of course, is the gravimetric one, because the gravimetric is characterized by a load cell on the bottom of the hopper that allows to get the best precision possible.
Yep.
Or the amount in terms of kilograms per hour they are loaded to the feeding system of the extruder. Then it can be, in certain case, substituted by a volumetric one that allows a good precision, but not as great as the gravimetric one. But of course, in this case, also the cost increase.
Yeah.
And then, according to the material, for example, if we are talking about the plasticide PVC, we usually configure the feeding system with the force doser, so with the vertical screws that force the material inside the feeding zone of the extruder in order to get the best filling rate of the screw and optimize the output and the quality of the material.
Thank you, Alessandro. The other one is, can you process recycled and virgin PVC with the same pair of screw, with the same design of screw?
I think that this is also a very important question, because you know that recycling is getting more and more the main target, one of the main targets of our customer, in order to reduce the cost and also increase their attention to the environment, of course. In this case, we don't have just a single answer, because also in this case it depends on the material. For example, if we are talking about recycling of window PVC profile, in this case we strongly recommend not to use the long extruder, especially if configured with the high compression and high shear screws, because in this case the risk of degradation or burning of material increases a lot.
Yeah.
In this case, we recommend the use of short LD ratio of extruder, so a short barrel length, and low-medium compression screw in order to avoid any risk of degradation of material. In other cases, we can use the same extruder, especially if the customer used to add the recycled material with, for example, a stabilizer.
In my opinion, it totally makes sense.
Thank you.
The other one,
We hope as well for the viewers.
I really hope.
We hope.
The other one is, in order to process different PVC pipe recipes on different extruder sizes, do you configure the same screw geometry? But in this case, I think they mean also ratio in terms of geometry.
Yeah, you mean compression ratio, yeah, if possible, yeah. This is another typical question from the customers. We have to be careful, because when we previously talked about certain compression ratio, we were referring to lab scale extruders. Okay. When, for example, we have to scale up the extruder for a certain material that has been already analyzed on lab scale extruder, it's possible that we need to increase the compression ratio, so to change a little bit the geometry of the screw if compared with one that we used with good results on the lab scale extruder. Okay. Why? Because of course the the volumes of material involved in the process on industrial scale extruders can't be compared with the small one involved in the lab scale extrusion process.
Okay, the other one is, what type of cooling you are using to stabilize the temperature and avoid the overheating of the tips?
This is another good question. I think that the customer in this case is referring to the screw tips. Of course, we have our typical cooling system for the screw. There is an internal circulation of silicon oil. This circulation is thermally stabilized through an external centralin. There is cooled itself by water.
And heat exchanger, yeah.
Yeah,
The same for when you want to cool the barrel with silicone oil. You have an external control unit and the oil circulates around the barrel and cools down the extruder. Otherwise, there is a solution with fans. So it's more or less, let's say, we use oil for both the applications.
Yeah, and according to our experience, this is one of the best systems to control the thermal
it's more effective.
Effect on the material, avoid degradation. Together, of course, with the use of fans or cooling of barrel, and prevent any kind of overheating on the screw tips.
Ladies and gentlemen, actually we finished this session. Again, I would like to thank you for attending to this event. We are going to answer to all your questions, and if you have any suggestion for other webinar, we'll be very happy to set up and organize another webinar. Thank you very much for your time. Have a nice one.
Bye-bye. Thank you.
Bye.